All right, ladies and gentlemen, welcome to Energy Week. Okay. Middle schoolers, your 7th grade teacher, maybe your 6th grade teacher talk about energy at all? Yeah. You're not high school, I'll ask you in a second. Talk about energy? Just talk about hydroelectric energy? Solar energy? Power plants? Nuclear power energy? Almost got it, missed it. Did you guys talk about potential energy? Kinetic energy? Did you calculate it? What's the unit for energy? If you calculate it, you'd know that for sure. Seems to be that most people have done a little bit of energy stuff, but some people haven't calculated it. Spence, high schooler, your middle school experience, did you calculate potential and kinetic energy? Did you find the speed of an object? We'll see. Okay. This week might be a breeze for you then. Okay. Should we talk about thermal energy and friction?
Yes.
I'm not sure.
We'll see. Okay. Since I don't know what you know and I do know what you don't know, okay, we're going to be taking it from square one. So with that being said, here's what we're going to do. We're going to do a Pendulum lab first thing. It's also butted up next to a Ninja Star lab. So tomorrow, if you notice, there are some zip ties attached to the ceiling. More of them around the room. So there's going to be 6 pendulums when you come in here tomorrow. Please do not touch them until I let you. All right? You're going to be doing some labs based off of this. First one being is, do you trust science? So if you take the pendulum and you bring it up to your nose and you let go. If you trust science and everything that it says, this pendulum will never hit your face. Unless you decide to be silly. What I see some people do is they'll do this. They'll go. And then lean forward, okay? You're going to clock on the teeth that way. So when you do this, make sure your back is straight. Bring it to your nose. Drop it gently. The better your release, the closer it's going to get to your face, all right? So if it's like down here, you had a bad release. Okay? The best I got were the carabiners I bought from Walmart, all right? You can get about this close to your face. All right? So if we understand science, we know it's never going to hit your face. Then we're going to do Ninja Star Lab. So what you're going to do is you're going to take popsicle sticks, you're going to store the potential energy in them, and you're going to throw them against the wall, and then they explode. Why do they explode? It's because of the way you store energy in them. When they hit the wall, kinetic energy goes flying. Then you got a little simulation with a dude on a skateboard, all right? And then there's a little bit of a tennis ball drop. All right. Tennis balls are, I could teach almost the entire semester with just dropping stuff from 2 meters. All right. So, any questions about what we're doing? The only thing I'm going to say is your homework, don't start it yet. Should be available for you anyways. I found some problems with it. So I'm going to go back to it tonight and revisit it. So after you get done with notes, you can work on the pre-lab of the Pendulum lab. Okay. So what is energy? Renewable energy, I'm a big fan. Get it? It's a windmill. It's a giant fan. There you go. We aren't going to hit up as much on like maybe what you did in middle school with hydroelectric energy, chemical energy, biochemical energy, thermal energy. We will hit up more specifically on kinetic and potential, which some people have already talked about. Totally fine. But we're also going to calculate. We're going to understand the numerical values of those energies. Okay? We good here? Comments, concerns, questions? Nope, I'm moving on. I already lost one of my markers today. Is this one going to work? Hey, look at that. Okay. Law of conservation of energy says energy cannot be created or destroyed. Anytime you see a law in science, you cannot break it. It always holds true. Okay? Energy cannot be created or destroyed, but it can go from one form to another. But the total amount never changes. That's a big part I want you to understand. That the total energy in a system will never change. So if you start with some energy, you're going to end with that same energy, but in different forms. So when you're typing up and answering your lab stuff this week, some no-no words. Creates, makes, whips, ups. Right? If your words explain that your energy comes out of thin air, right? That's some no-no words. All right? By the way, I think this is like the very first slideshow I made when I was teaching 5 years ago. So it's got some memes and references in there that are a little bit dated. I still think they're funny to this day. You may not. I'm just forewarning you. Legitimately. This was 2015. Where are you guys in 2015? All of you are still in elementary school. You guys are fourth graders. That was a while ago. Spencer's doing math. Okay. So energy cannot be created or destroyed ever, ever, ever. However, it can transform from one type to another. All right. Good? No? Okay. Hannah, you doing okay today?
I'm really tired.
Really tired? I feel you there. I got up at 2 this morning.
Oh my gosh, why?
I just couldn't sleep. I feel you.
I do that like every
I
night.
feel you. But I'm here and I'm ready to roll. So I'm glad you're here and ready to roll too. Okay. I was just so excited about this lesson today. I can't sleep. No, it wasn't it.
Were you dreading this lesson too much to sleep?
No. I don't think I will ever dread teaching you guys. I don't think I've ever dreaded a lesson. I've been tired coming in. I don't think I've ever dreaded it. Good?
Yeah.
Okay. So what is energy exactly then? All right. The first bullet point is the most important. I'm going to talk about the next two. You don't necessarily need to write them down. Okay. This is the important part. Energy is the ability to do work. So when I put gasoline in my car, all right, it gives my car the ability to go farther. Does it necessarily have to do it in the moment? No, but it has the ability to do the work. Everything in the known universe is either matter or energy. So does anybody know about the scientist that connected the two? His very famous theorem, postulate, E equals MC squared. What is it, Dallas? Albert Einstein, absolutely. He connected the fact that matter and energy are connected, that there is a relationship between them. He found out if you take one paper clip, I used to have paper clips to show, but I don't have paper clips on my desk right now. If you take one paper clip and you convert it into pure energy, if you figure out how to do that, not only will you basically outprove any scientist currently in today's standards, but you'll also probably become a billionaire, if not a trillionaire overnight. The world's problems really just revolve around energy. How do you get it? How do you use it? How can you create it? If you manage to figure out how to do that, we won't need to have gasoline cars anymore. We'll have whatever you figured out how to make paper clips into energy cars. So, big, big money there. Stop climate change. Stop using as many resources as we do. Right. Okay, I'm not going to go further into that because that can get really crazy. I'm just going to say energy is the ability to do work. Okay, there? You get Spence?
Yeah.
You look so riveted.
Tired.
Tired? Are we good there? Okay. I'm going to exit out this one. We're not going to talk about chemical potential energy because that's going to be in chemistry class, which we might do next semester. Talk about chemical energy, but definitely not this semester. So I'm going to say is, all energy that we know breaks off into two potential categories. Potential energy or kinetic energy. Kinetic energy does go in a couple different directions from there, but we're not going to unpack that. For potential energy, the only thing we're going to unpack is gravitational potential energy and elastic. All right? So the pendulum, that whole system works off of using gravity to store energy. Elastic potential energy. All right, your ninja stars. You're going to bend. I wish I had the ninja star in front of me. You're going to bend the popsicle sticks, and you're going to form some ninja stars from that. By bending the popsicle sticks, you're going to store elastic energy in the system. The video shows like 6 different ones to make. Some complicated ones, some not so complicated ones. Some explode violently, some explode not so violently. All right. You're welcome. I just need to see you make one and talk about it. You don't have to make all 6. If you want to, absolutely you can. All right. So here's what I want you to brain is, this does get further in depth, but the only thing we're going to talk about is kinetic, potential, and then most of the time we're going to talk about gravitational potential energy. Okay? Good here? Trooper, you look riveted as well. You tired too? Okay. There's your first outdated meme of today.
I don't get it.
I don't either.
Do you know who the character is? I will put a dum-dum down. Somebody tell me who that character is.
Well, she's from the
White guy. Wait, Katniss
Who's
Everdeen or
this dude?
That guy.
Who's this dude? I'm in a moment of mourning. Give me a second.
No, that's a boy.
Yeah. Is that a girl or a guy?
That's a boy.
Katniss Everdeen's a girl.
This is
Guy.
Legolas from Lord of the Rings.
Legolas?
Legolas from Lord of the Rings. Oh man.
I know that's not Katniss Everdeen. I've seen her.
Katniss Everdeen is a girl from Hunger Games.
Yeah, I know that. I don't
Yeah.
know who that is. I don't watch Lord of the
That
Rings.
hurt. Your unofficial homework assignment is to go home and watch Lord of the Rings.
No, I already
And
watched
then you
that.
can be tired coming to class if you watch all of them.
No. Can I take it? Not.
Okay.
Sounds terrible.
All right.
Sounds not.
Man, that hurt. That hurt right here. Okay, let's talk about potential energy then. Potential energy is energy that is stored, or just energy that's stored, but it can be stored in one of 2 ways. It can be stored based off its position or what it is. So if I take this pendulum and I just rest it, just hanging down, all right? There's a little bit of potential energy between the bottom of the pendulum and the ground, just a little bit. But what I can do is I can take this pendulum and I can store more energy in it based off its position. The only thing I've effectively done here is changed its height. So by changing the height of an object, you can change its potential energy. All right? Same thing as holding a bowling ball above your head. All right? There's a potential for the bowling ball to hit you. Will it? No, but it has stored energy in the system. What's an example of food that is not necessarily based on position, but based off what it is? And that is food. So when you eat an apple, or whatever you're going to eat for lunch, or ever have for breakfast, all right? I'm willing to bet some people who are maybe tired today didn't eat breakfast.
I never eat breakfast.
There you go. Why should you eat breakfast? It's because the energy that is in your food gets digested by your stomach, allows your body to wake up and do its motions. All right? So the energy that your body uses. Sounds like Christmas over there.
I know.
Okay. All right. Same thing as food, as in dynamite. Does dynamite explode on its own? No. But it is stored energy in such a way that based off of the chemicals inside of it, when you light it on fire, it tends to explode. Okay? We're only going to look at gravitational potential energy. All right? There's only one new thing on this slide, and that's energy and what we measure it in. And that is joules, written by a capital J. Everything else on that slide you now already know. You've got mass, which is in kilograms. You have gravity, which is meters per second squared. It's acceleration. You have height, which is in meters. There's one small caveat. What number do we use for gravity? Negative 9.8, except for this formula. And I'm going to show you why. If we used negative 9.8, here's what the formula would look like. And you were to Google potential energy, you might get this formula. This is the true representation of potential energy. Delta U sub G equals mg delta Y. That can be hecka confusing. Okay? So what do we do instead? We ignore all of the variables. We erase this. We go. Okay? And instead, we just use positive 9.8. And with that being said, we don't get so confused upon what the other variables represent on the negative signs of both sides, things like that. Right? Or you can use positive 9.8 if you ever get lost. All right? We now have another poster. Potential energy is right here, and I even remind you, G is positive 9.8. Okay. So when you're using the reference here, MGH, positive 9.8. Cool. You might run into a problem like, whoa. My energy came out as negative. Nothing can ever have negative energy. At bare minimum, it can have 0. But it can never actually truly have negative energy. What it can is lose energy, but we don't talk about in this class. We save that for like regular chemistry or physics class. That's a little bit more higher depth than what we're going for. So we're just going to use MGH and call it done. Good there? Okay. So let's try this one out. What's that?
What are they doing?
Okay, we'll give you the formula, so let's go from here. We got gravitational potential energy, which is P equals mgh. Great, you ready? Do I know potential energy? No. Do I know mass? What's my mass? 40 kilograms. What's the gravity? 9.8, fantastic. And then what are we going to use for height? 300. Do you see why I let you use the calculator now in class? I mean, unless you're welcome to try to do that mental math. You want to do that? No, I don't want to do it either. Okay. So we pull out our calculators. I really recommend if you were to go ask mom and dad, hey, can we go buy a calculator? You go buy one of these. Okay. This is probably the most valuable calculator I've ever seen before, except for the graphing ones. The graphing calculators can be like $100. There's a reason they're $100. These calculators have like $15 to them. They're super helpful. The reason I recommend this one, all right? There are other ones that are absolutely totally valid, but if you don't have one yet, and you're gonna go get one for your high school and for your college career, I really recommend this calculator. All right? The reason being is because it is a 2-line scientific calculator. As I punch in my numbers, I can see my numbers. When I hit the enter sign, my what I punched in is above it, my answer is below it. A lot of calculators, once you hit an equals, it'll take away what you typed in and then show you your number. We're like, well, what if you typed in something wrong? So for example here, if I typed in 40 times 9.8 times 3,000, and I'm like, oh man, I got a really big number. That doesn't seem right. You can press up, you can go back to it, and you can fix your mistake rather than having to type everything in. Okay? I really recommend these calculators. So we get potential energy equals 117,600. And then what's the unit for energy? Grade? What is it? You don't know? Give it a shot. I know it's in front of you. No. What? Joules. Okay. Joules, which is denoted by a capital J. Go ahead and still help me out though. You ready? You gotta catch it, man. All right. The metric system uses joules. Does anybody know what the English system uses energy in? I'm willing to bet you do, but maybe you don't know you do. Yes, Vince?
Newtons or Newton something.
Newtons are force. I like where your brain's at. We're going to talk about forces after fall break. We're talking about energy. Yeah, Dallas? Volts? Jolts? No. Volts are a thing. I've never heard jolts. Jerk's a thing in physics class. Something everybody knows. Everybody knows. You just don't know you know it. Hannah, if I'm going to go on a diet, what am I going to count?
Calories.
Count calories. Not even count your pounds. You can look at your weight, absolutely. But if I'm going to go on a diet, I'm going to count calories. Why am I going to count calories? Because my food intake is based off the energy stored in it. So a high fat, high energy, high sugar food is going to have a lot of calories. It's because it's had a lot of stored energy. Okay? All right, try this one out for me. I am going to change this to be 17.5 rather than 175. And this is 36 rather than 0.36. Okay? Yes, Jacob.
I've heard like you actually burn more calories eating celery than you get from it.
True. Okay, but that doesn't pertain to what we're doing here, okay? All right. Plug and check. See if you can get it. Nora, you doing okay today? Did you have your coffee? Oh, makes sense. You're not jittery. All right, how high from the ground is the apple? We're looking for what, Garrett? If we're looking for how high the apple is, what are we looking for? What variable?
Height.
Height, fantastic. Find height. Yes, 17.5, not 175. I found out if I gave it 175 joules, the tree had to be a ridiculous height, like half a mile. Now it was a quarter-mile high tree. That was a big tree. How high from the ground is the apple? P equals mgh. Want your shot at it? Kind of.
I think I know what I'm doing.
Give me my numbers. Do I have potential energy?
Yes.
Yeah, what's my potential energy?
17.5.
17.5 joules, absolutely.
I just didn't know what order it was.
What is my mass? Yep. What's the mass?
36.
All right. We run into a problem.
Well, you have to have your number. 8.
We run into a problem. You're given 36 grams. Looking in your notes, maybe you wrote it down. What does mass need to be in when you're using the potential energy formula? What? Kilograms, fantastic. So we have to convert 36 grams to kilograms. We're going to do it off to the side right here. And then we're going to use this number right here. Ready, Wyatt? $36 grams, we have to convert it to kilograms. Hannah, do you remember converting stuff? Let's try it out. You ready? I got grams on the top left. What am I going to put on the bottom right? Grams, absolutely. And what am I going to? Kilograms. Absolutely. And how many grams are 1 kilogram? 1,000. Fantastic. 1,000 over 1. So I'm going to run over my calculator. That's all we got to do. Grams and kilograms. Am I going to divide or multiply here? You're doing so great. We just hit a brick wall. Absolute, let's divide. Numbers on bottom, so we're going to divide here. 36 divided by 1,000 gets me 0.036 kilograms. All right. Now let's use mass. Ready? I'm going to pick up where you left off.
So it'd be
0.036. What number do we use for gravity?
That's the 9.
That's 9.8.
That's what I was wondering.
And do I know height? Sure don't.
So you multiply.
There is more than one correct way to do this.
Can you just multiply the 9? Multiply 0.036 times 9.8 and then divide it by 17.5.
You're very close. What came out of your mouth maybe was not in your brain. Okay. All right. Ellie, you want a shot or am I going to decide? Sure? What are you going to do first? Multiply what?
0.036.
Absolutely. I'm going to take, no, this doesn't change at all, so we get 17.5. So here, we run over my calculator, we type in 0.36. 0.036 times 9.8. I get 0.3528H. What do you want to do now?
Divide 0.3528
On both sides? Absolutely. 0.3528. Oh, try that again. Board's being a little slow today. Well, it's not the board, it's the computer.
This is really to fix my mouse.
Fantastic.
What was wrong with it? It didn't work.
I get a height of 49.6 what? What's the unit for height? What's that? Meters, fantastic. All right. Looking good here? Any questions? Comments, concerns? Am I just that so boring that you want to turn around and your body's physically turned backwards? Don't disrespect me like that. Okay, kinetic energy. We're going to switch gears a little bit. All right. We're going to switch gears a little bit and talk about kinetic energy. So you take potential energy and you can convert it into kinetic energy. Sorry, I got one on backup. Okay. So when I put potential energy into this pendulum and let go, that energy is not destroyed. What does it do? It turns into kinetic energy. It's the energy of motion. So, when you have anything moving, I don't care if it's down to the smallest particle, atoms, or the largest things we can find, planets, or even planetary systems, everything moving, anything moving has kinetic energy. Ooh, I want to see if your middle school teacher taught this. What happens if something has zero kinetic energy? Somebody know? Yeah, Wyatt? If you knew it, I'd be legit impressed.
Is it the one where like you're about to go down
No. We'll get there next semester. We might get to it. I'm just curious if you know it, Wyatt. I see where your brain's at, but that's not quite what I'm asking. Yes, Vince?
It's not moving.
Close. We'll get there. We'll get there. We'll get there.
I have another idea.
All right, what's your other idea?
Absolute zero.
Absolute zero, fantastic. Absolute zero is when everything stops moving, even atoms. It is the coldest something can get. So that's a perfect little tangent of that temperature. When you measure the temperature of something, right, it's actually a measurement of how the atoms are doing. The hotter the atoms are, the quicker they move. If you get atoms so cold that they stop moving, it's the coldest something can get. We call that absolute zero. Fantastic. Big brain. All right. Energy and motion in the form of doing work. This is awesome. That means comes next week. You guys are doing great. I think this week's going to go pretty smoothly. You good, Piper? Cool. Is this a review for you? A little bit, maybe a little bit building on? Perfect. If we hit that spot every week, we're looking great. There's another dated meme for you. Oh. Try that again. All right, how do you calculate kinetic energy? Now our formulas are starting to get a little bit uglier. On the yellow poster, it is still there. It'll always be here. Okay. Spence, can you catch?
Yeah.
What are you taking 1/2 of?
What's that?
What are you taking 1/2 of?
1/2 times mass times velocity squared. It's just 0.5.
So just basically half the mass.
Half the mass times velocity squared.
Would the square undo half?
No. I see where your brain's at though. But no. Kinetic energy is still measured in joules. Mass is still in kilograms. Velocity is meters per second. All that stuff we've been doing. Look at that. It keeps showing back up. It's popping its ugly head up. All right. The only thing I see students do wrong is the squared here trips a lot of people up. Either take it the squared or the square root or dividing by a square, and it's just like, whoo, man. You show me your work though, and I can show you where you went wrong if you went wrong at all. Okay? The homework, all right, is not up yet because I found some problems with it. However, when it is up, I'm going to stick with the same policy I did last week. Okay? That's because I still got a vast majority, not a vast majority, I got way too many people just abusing the system. So with that being said, all right, you show me your work for the homework, I'll show you which ones you got wrong. The homework will no longer show you which ones you got right or wrong. You still have 20 attempts, but it won't show you which ones you got right or wrong. Okay? We good here? All it is plug and chug.
Don't want me to tell you your score?
It'll tell your score, I just want to tell you which ones are right or wrong. Nope, that's problem number 2. It's double clicking on me today. What is kinetic energy of a jogger with a mass of 65 kilograms? 65 kilograms, that would be a person who's approximately 130-ish pounds. Let me see specifically, I'll let you know. 65 times. 143, sorry. 143 pound individual running at a speed of 2.5 meters a second, which is a pretty solid jog, is going to have how much kinetic energy? You tell me. Garrett Trooper, I'm coming for you. Just be ready, okay? You're going to have to decide between the two of you who's going to go first, though. Trooper's going to go first?
Yes.
All right, Trooper. Ready? Kinetic energy formula, what is it?
Half, 1/2 mv squared.
What goes in front? You just told me 1/2 mv squared.
K equals.
K equals 1/2 mv squared. All right? Do I know kinetic energy?
Yeah, no.
No, we're looking for it. 1/2 is 1/2. Can't change that number. What's the mass?
65.
65.
And 2.5
2.5
squared.
squared. Oh, try that. 2.5 squared. Cool. Here's why I love these calculators. Right? They're great. All I can do right now is in one get-go on my calculator, I can just type in 1 divided by 2, which is 1/2, times 65, times 2.5 squared. Do it all in one get-go. I can even see if I did it right. I really recommend these type of calculators. If you don't, you're going to have to square it and then multiply. All right? So K equals, rounded, 203.13. And then what's the units for energy, Garrett? Joules, which we denote by a capital J. Okay. Trooper, you ready?
Yes.
Sure. What a snack. We good here? Any questions? All right. Let's talk about this pendulum. I'll leave the second examples warm for tomorrow. This pendulum, when I let go, has how much energy? I need this. Let's put it at, that's 1 meter, 155, 1.55, right? 1.55 meters to my nose. All right, it's 155 centimeters. So we can calculate the potential energy to my nose. However, okay, it doesn't go to the ground. Follow me there? So if I look at my height here, my height is going to be 155 centimeters minus 10 centimeters. So my height is actually going to be 1.45 meters. Okay? That's the height at which the pendulum is swinging. The mass of the pendulum, it's written on there, I believe. 250 grams. So the mass of the pendulum is 250 grams. Uh-oh, Hannah, what am I going to have to do? Convert. All right. 0.25 kilograms. For the sake of time, I'm just going to go ahead and convert. All right. So here's what we can say and we can calculate is we know that the potential energy we can calculate stored right here is going to be a certain number. All right, let's find that number right now. Mass is going to be 0.25. Gravity is 9.8. And my height is 1.45. Run out of space. So the potential energy, when I bring it to my nose, is 0.25 times 9.8 times 1.45. 3.6 joules of stored energy. We good there? I just did what calculation we did earlier. Find the potential energy. Well, energy is not created or destroyed. Garrett, come back to you. You got away with an easy one with the unit. I'm going to come back to you for a harder one. All right? Can energy be created or destroyed?
No.
No. So when that 3.6 joules of energy moves the pendulum, all of it becomes kinetic. So how much kinetic energy do I have at the bottom of the swing? 3.6 joules of energy. Because energy is not created or destroyed, right? When it swings back up, Garrett's going to be super tough. How much energy is in the pendulum? 3.6. So the total mechanical energy in the system is always going to be 3.6 joules. If what didn't exist? Well, if gravity didn't exist, I'd like the pendulum, it would just stay there. Garrett, I'm going to come back to you. Ready? As this pendulum's swinging back and forth, it is getting slower and slower, and it's getting lower and lower. I'm losing energy. Like, wait, Mr. Williams, you just told me energy can't be created or destroyed. What's going on here? Where am I losing my energy at? Got an idea? I'll give you a hint. Starts with an F. Rhymes with friction. Friction. We have air friction going on here. So you lose the energy in the system. Think, okay, you lose the energy in the system because of air friction. All right? But here's what I know. When I bring this up to my nose, it'll never hit my face because when I let go, it's got 3.6 joules of energy. It will never have more than 3.6 joules of energy, so it'll never hit my face. All right? There's going to be 6 pendulums hanging around the room coming tomorrow. Please don't touch them until I tell you to do so, because people are going to be walking about. Since people are going to be walking about, what I really recommend you do is being very careful. All right? Any questions here? All right. Fantastic. If you want to, you can have the pre-lab done before you come to class tomorrow. Until then, see you guys. Bell's going to ring in 2 minutes, 3 minutes.